Hi everyone, my name is David Klee, founder of Sequilibrium. Welcome to Module 7 of my course, the SQL Server on VMware Accelerator. We just wrapped up a good overview of the host hypervisor cluster in this bootcamp. Now it's time to go through all of the pieces that make up your SQL Server virtual machine. Let's dive in because this is going to be a long one. This module is going to guide you through every component of the virtual machine and how to tune them for maximum possible SQL Server performance. We're going to start with discussing what actually constitutes a virtual machine, and then move into the hardware compatibility and firmware type of the virtual machine, and then we're going to spend quite a lot of time on the virtual machine CPU configuration. We'll then talk about memory, network adapters, and then a lot about virtual disks. We'll then get into some odd situations around hypervisor host interoperability and things that you can do ahead of time to prevent these things from knocking your SQL servers offline. First of all, what actually is a virtual machine? Technically speaking, it is just a key value file that contains all the properties that constitute your virtual machine settings. These can include how many CPU cores you have, how much memory we have assigned, or where your hard disks are at on the VMware shared file system, or even odd things such as what operating system did you tell it is installed. It's essentially a key value descriptor file on the VMware file system, nothing more and nothing less. You can see on the screen here an example of the VMware virtual machine definition called the VMX file. There's a lot that goes in here, but it's honestly pretty dull, and we can see everything we need from the front-end GUI. One of the bigger things that the descriptor file points out is where our virtual disks are at, which are other just large files on the VMware shared file system. You can see these as VMDK files, or virtual machine disks. You'll also notice that there are other VMDK files that contain a .ctk suffix. These are change block tracking files that are useful for understanding what has changed on the virtual disk so that I can back it up quicker. This virtual hardware list contains all of the essentials that you would have on a regular server. You have virtual CPUs, virtual memory, virtual disks and disk controllers, even virtual optical drives that you can put fake CDs in. You also have communications means like virtual network adapters. This is all of the virtual hardware that is, quote, seen as real hardware by your guest operating system. It doesn't know that it's emulated and not directly present in that physical machine. The scale at which you can assign these resources is incredibly high. At the time of this recording, vSphere 7.0 Update 1 allows virtual machines as large as 768 virtual CPU cores and 24 terabytes of RAM. That is a monster virtual machine. You can also connect a high number of virtual disks, each as large as 62 terabytes. You can have 4 of each type of disk controller, SCSI, SAS, and NVMe. We'll talk more about that in a little bit, and make sure to ignore the SATA and IDE controllers as they are horrible for performance. With these maximums, you can assign a tremendous amount of resources to a virtual machine. That's not to say you should. You need to assign what it needs, nothing more and nothing less. We're going to go into great detail about this in the performance module. VMware has a virtual machine hardware compatibility level that should be kept up to date. It's somewhat similar to a SQL Server database's compatibility level. The newer the virtual machine hardware compatibility, the more benefit you can get by taking advantage of the new and updated features that accompany that version of ESXi. I find that the vHardware compatibility levels are generally left alone by virtual machine administrators, and that is what the official guidance from VMware tells them to do. Contrary to their guidance, I always encourage people to keep the vHardware version to its absolute latest. It should be set to the highest possible level for performance, but if any of the physical machines that this VM might run on, including disaster recovery facilities, are running an earlier version of ESXi, the hardware compatibility level should be set no higher than the lowest version accessible by these servers. You cannot run a VM with a compatibility setting newer than the maximum compatibility of the ESXi server that you're running on. You'll notice on the screen that compatibility level for this virtual machine is set to ESXi 7.0 or later VM version 17. If the host is running ESXi version 6.7 with the latest update, the compatibility level maximum is version 15. If it's not yet update 2, then the max is version 14. But I'll tell you right now, if you're not running update 2 on 6.7, they need to get their butt in gear and actually go update that. A small outage window is required for updating this compatibility level. The VM is turned off, then the virtual machine administrator runs a quick function that updates the vHardware from the vCenter GUI. Care should be taken to make sure that the virtual machine is backed up prior to this operation. While I haven't seen any issues with this in quite some time, I never want to guarantee that this is going to work properly on the first try. Another feature that needs to be set at the virtual machine prior to an operating system getting installed is the firmware type underneath the boot options in the VM options setting. The default firmware type for almost 2 decades now has been type BIOS. However, the EFI firmware type is now an option. EFI firmware types are more modern and have a number of security benefits. Microsoft has recently announced that future versions of the Windows Server operating system will need an EFI firmware type as a requirement because they will be enabling a feature called Windows Secure Boot by default. That feature cannot be enabled without the presence of a trusted platform module chip. That chip is not emulated for the virtual machine unless the firmware type is EFI. This setting must be set prior to the operating system being installed, as you cannot change this afterwards. If you try, the operating system inside the guest will not boot successfully. There are a few hacks to attempt to make this work, but it'll put your virtual machine into an unsupported state, and that is not supported by both VMware and Microsoft, and I will not ever encourage you to do that. Most of the time, I find that the virtual machine templates that your VM admins work from when deploying new servers for you are built with the legacy BIOS type firmware. Encourage them to build a new template with the new firmware type set to EFI. As they start to deploy new virtual machines in your environment, this firmware type will start to be deployed with it. Over time, the legacy firmware type will start to phase out. If the Windows Secure Boot feature is ever needed or required from your security teams, you're ready to go. If it's never required, the worst thing that'll happen is that your virtual machines will boot a few seconds faster. Another setting that is occasionally overlooked is to assign the guest operating system version type. Most of the time, this is set just fine. Occasionally, I find that this is overlooked. Some things about the virtual machine are treated a little differently by the hypervisor, and if the guest operating system type or version are set incorrectly, you might get some odd behavior inside your virtual machines. I saw this before where a few hundred Windows-based virtual machines were all set to the guest operating system type Red Hat Linux. We had unusual behavior with network packets being dropped. Once we powered off the virtual machines and changed the guest operating system assignment, these anomalies just disappeared. Again, it's rare to see this setting set incorrectly, but it's worth checking if you're already into the virtual machine configuration. Next, we're going to discuss one of the most commonly misconfigured components of the virtual machine. I'm talking about the virtual machine CPU architecture. It is nowhere near as simple as virtual machine administrators think, and incorrect settings or values here can result in a dramatic performance problem for your SQL servers. Usually, your virtual machine administrators are quite busy with their day-to-day tasks. When they spot check their servers, they're looking primarily at a macro level at the amount of CPU and memory consumed per host. This point of view tells you almost nothing about what is actually going on with the CPU schedulers and the impact to the virtual machines. Micro-level insight is needed for your critical SQL servers, and chances are they've not had the opportunity to drill into this layer, at least on a frequent enough basis, to detect any issues. The virtual machine configuration for CPU presentation is arguably the most important piece to get right with your SQL Server virtual machine architecture. I'm going to spend a lot of time on this topic because your SQL Server licensing depends on the number of CPU cores either assigned to this virtual machine or are present in the physical machine host. We have to get this right. We spent a lot of time at the physical machine module talking about vNUMA. On a physical machine, you have any number of CPU processing cores per socket, and probably more than one CPU socket to accommodate. The same thing goes for your virtual machine. You have the ability to define a number of CPUs assigned to the virtual machine. You also have the ability to set the number of cores per virtual machine socket so that you can align the virtual machine better with the physical machine CPU topology. We'll call this vNUMA. SQL Server is very vNUMA aware, and so are your licensing limitations, so we must align our SQL Server vNUMA appropriately to your physical machine vNUMA topology. Making sure that the vNUMA aligns properly is critical to ensure that our vCPU scheduling is kept to a minimum performance overhead. Like I mentioned in the very first module, every single thing that happens inside a virtual machine with its compute resources must traverse the hypervisor's resource scheduler to gain access to those compute resources. We must minimize both the number of objects in the queue and the time spent in the queue in order to maintain peak performance. I'll remind you about the vCPU scheduling process. When you run a command inside the virtual machine, it doesn't know that it's a virtual machine. So it thinks that when you execute a command, it just finds those physical compute resources and runs. However, because of the hypervisor, there is a bit of CPU scheduling cost to get that command onto the hypervisor scheduling queues. There's a certain amount of time spent in the scheduling queue. That amount of time spent waiting is called ready time. It's ready to run, but it can't get there yet. Finally, it starts to run, but the runnable state could be interrupted and cause the tasks in the queue to both be paused, or it may rebalance so that the individual CPUs are more closely aligned. There could also be efficiency losses due to hyperthreading or power management going on the physical CPU package. Finally, the command gets executed. Done right, this entire process should take less than half of 1% penalty or less. Done incorrectly, this can be the biggest silent performance killer in your environment. I've said it before, but the very first thing that we need to worry about is minimizing the number of objects in the queue. That means assigning the appropriate number of virtual machine CPUs to that virtual machine. Because this is a virtual machine with scalable resource allocations, we don't have to assign the number of compute resources that we'll think we'll need by the time this hardware is due to age out. We need to start getting in the habit of assigning the resource allocation that we need now, with appropriate headroom, of course. Doing so usually reduces the number of objects in the queues. The less objects that we have in the queues, the less objects the hypervisor has to manage. We're going to go into significant detail on this topic in Module 11, where I show you how to not just understand right-sizing, but learn how to detect key metrics inside the hypervisor that'll help you realize when things are not properly right-sized. The act of right-sizing the virtual machine is rather complicated, but with a little bit of perfmon or sysstat work, we can get a really good baseline of what is actually consumed. Again, we'll do a deep dive on this in Module 11. Okay, let's now talk about how to properly present CPUs to these virtual machines. The virtual machine has the option to present a certain number of CPU cores to the virtual machine and to define a certain number of sockets with cores per socket. Your virtual machine administrators might think that you can assign logical cores, but the hypervisor tends to not use them unless there is significant CPU pressure. Leave hyperthreading enabled on the physical machine, but do not factor these cores into your maximum core count per socket available to you. My personal preference here is to provision only up to the number of cores that exist in the physical core count, not including the hyperthreaded ones. These CPU cores are seen by the guest operating system as regular CPUs. There actually is a small parameter that Microsoft adheres to called the Open Virtualization Standard. The virtual machine layer can tell the hypervisor the number of sockets, and this is what is read and displayed in the task manager as the number of sockets. I'll be the first to tell you that this socket count display could be inaccurate. More on that shortly. I'm going to sound like I'm preaching, but virtual machine NUMA is very frequently misunderstood and misconfigured by your virtual machine administrators. Most virtual machines do not change their performance characteristics if this is misconfigured, so things just generally work for them. For your SQL servers, nothing could be further from the truth. The reason that vNUMA matters so much is that NUMA management has significant overhead at every layer of your infrastructure stack. Working from the bottom up, the physical CPU management has local or remote node lookups for both CPU and memory. The hypervisor layer has context switching and NUMA management for memory and CPU workload assignments. Your operating system has to do the exact same thing. So does SQL Server. I'm going to let you in on a little secret. VMware vSphere 6.5 made some changes to vNUMA management. There is a chance that it may not listen to you when you assign a certain number of cores per socket. The following guidance is accurate if the ESXi version is at least 6.5 and the vHardware compatibility version is version 13 or above. The front-end GUI allows you to assign the number of CPUs and cores per socket and then calculates the number of sockets. This is displayed in the management interface, and what we select is what we usually get. It just doesn't listen to you at all. What it actually does is reviews the number of physical cores per physical socket. If the number of virtual machine CPUs that you've assigned a virtual machine is equal or less than the number of physical cores in a single physical socket, then no matter how many sockets you've assigned to the virtual machine, you only get one socket with that number of virtual CPUs assigned. It does not display this on any front-end screen inside vCenter. It does this because vNUMA assignments have been misunderstood for so long, they felt like they know better than us. And for the most part, it does get it right. Occasionally, though, it doesn't get it right. What this means is that we have to be incredibly careful about what is actually presented inside the virtual machine versus what is configured at the virtual machine layer itself. We'll be discussing this in detail throughout the rest of the module. Prior to vSphere 6.5, or if your vHardware compatibility level is set earlier than version 13, then vNUMA management changes. If your virtual CPU count is greater than 8, then it would listen to you with what you assign the virtual socket count. If your virtual CPU count is less than or equal to 8, it would assign one socket, no matter how many you had told it to. Also, if you assign a specification for 1 core per socket with the socket count equal to the number of CPU cores, that was your way of manually telling VMware to automatically manage virtual machine NUMA. I'm going to assume that you're running a more recent version and compatibility level than this, so I won't spend that much time on the legacy architecture. If you are not, get your VM up to spec, and then you'll notice these changes. To properly understand vNUMA, let's assume that we have defined a right-sized vCPU allocation for the virtual machine. If the number of virtual machine CPUs is less than or equal to the number of physical CPU cores in one CPU socket, assign only one virtual socket to that virtual machine. The hypervisor will do a very good job of placing it on one physical NUMA node and keeping it there so that all your memory access is local. If the virtual machine CPU count is greater than what exists on a physical CPU socket, split the virtual machine down the middle and review. If the core count per socket is still greater than what exists in a physical socket, subdivide it again and re-review. This is essentially the process that the hypervisor is going through automatically. I'll tell you firsthand, though, that while the hypervisor is actively checking the CPU core count, it is not looking at the memory assignment. What this means is that if the virtual machine CPU core count fits comfortably inside one physical CPU socket, but the virtual machine memory assignment is larger than what exists on the physical machine NUMA node, you end up with a NUMA imbalance because the hypervisor is not looking at this memory metric. The virtual machine memory is now split between physical NUMA nodes, but you'll never tell this from inside the virtual machine. The only way to actually see this properly is to SSH into the host and use a command-driven tool called ESXtop to see the NUMA memory placement for the virtual machine. This demo is a rather specific demo, but if you have any need to specify your virtual machine NUMA if the VMware layer is doing things that you didn't expect, this is how you go do it. This specific example is if you have a virtual machine where the CPU footprint fits inside one physical NUMA node, but the memory footprint does not. So we're going to get started by just taking a look at this virtual machine's configuration. You can see we have 12 CPUs and 256 gigs of memory. A pretty good sized virtual machine. Now the host that this is on is a 24-core machine with 384 gigs of RAM. So that means the memory footprint spills over one physical NUMA node, but the CPUs do not. Now this virtual machine is named Lab 11, but it's actually a clone of Lab 01, so when you see that, don't freak out. We're going to start up SSMS, and we're going to take a really good look at what SQL Server is seeing here. Now, once our instance is up, right-click on the instance, hit Properties within SQL Server Management Studio. Go to Processors, expand the word All, and you see we have one NUMA node with 12 cores. Not exactly what we want because we know we have a NUMA imbalance. So we're going to go shut this machine down. Okay, if you edit the virtual machine, we're going to go specify virtual machine NUMA so that we have 2 sockets, each with 6 cores. Okay, makes sense, right? Hit OK, power the virtual machine back on. And now you can see from the task manager here under performance, it is saying 2 sockets, 12 virtual CPUs. Okay, looks better, right? Now open SSMS. Right-click on the instance and double-check those NUMA settings. Go up under Processors, Thank you Updates, go to Processors, go to All, and you see we still have the one NUMA node, not what we told it to do. That's really unfortunate. We're going to have to go manually override this setting to make it do what we want because it just doesn't pay attention to us, and that memory imbalance is pretty significant. Okay, shut the virtual machine down. Edit the virtual machine settings. Go to VM Options, go down to Advanced, scroll down, and go to Edit Configuration under Configuration Parameters. Now you can take a look at this. There's a ton of information in here. This is all the information that's in your VMX file. You generally don't want to mess with any of this stuff, but we're going to add 3 values in here that are going to force it to do what we want. Now it's going to be small, so I'll put these up on the screen. NUMA.vCPU.follow cores per socket equals 1. Add another configuration parameter. CPU-ID.cores per socket, and we're going to set this equal to the number of virtual CPUs that you want in one virtual machine NUMA node, in this case 6, so we split the VM in half. Add another configuration parameter, NUMA.AutoSize.vCPU.max per virtual node. We're going to set this also to the number of vCPUs that we want in one virtual NUMA node. Once you've added this, hit OK. Then hit OK again. Now go ahead and power the virtual machine on. Windows is still showing 2 sockets, 12 cores. But let's take a good look at what SQL Server is showing. Okay, once we're in the instance, right-click on the instance and hit Properties. Then go Processors. Hit All. Look at that. We've got our 2 NUMA nodes properly. So now our memory is balanced with the physical machine NUMA topology. That's a big deal, especially from SQL Server licensing, especially from performance. Life gets better when these things are aligned. Your virtual machine administrators may try to disagree with you on the use of hyper-threaded cores for your virtual machine CPUs. In theory, you can actually assign the number of virtual machine CPUs up to the number of logical cores that exist on a physical machine. I encourage you to not do this. There are significant amounts of context switching penalties that can accompany leveraging these cores incorrectly. You can override this if you need to with the Prefer HT Advanced Virtual Machine settings set to true. If you feel like your workload will benefit from leveraging hyper-threaded cores, I cannot urge you enough to test this setting well before the time you go to production. Over my entire consulting career, I've only needed to enable this setting twice at the time of this recording to boost performance of a SQL Server. There's a blog post from VMware.com on the screen that you can read more at if you're really interested in exploring this setting. There's a handy little chart here to help you figure this out. Let's take the example server on the screen with a 2-socket by 12-core configuration and 384 gigs of RAM. Our physical NUMA node consists of 12 CPU cores and 192 gigabytes of RAM. If you worked on the list of virtual CPU and memory assignments, you'll find that it's fairly straightforward to make sure that our virtual machine aligns properly. Smaller virtual machines will fit comfortably onto either physical NUMA node, so we're balanced properly. But when you hit the state where the VM fits into one socket but the memory does not, we're now imbalanced. When you get to the extreme machine down below with 32 virtual CPU cores and 320 gigs of memory, technically we're aligned, but we're now leveraging hyper-threaded cores and could run into significant context switching overhead that could perform poorly. For the virtual machine administrators out there, there is a console-based command that you can run to verify your virtual machine NUMA topology. You can thank a performance tuner from VMware Corporate named Valentin Bonzio for the script on the screen. It allows you to verify physical machine NUMA placement for your virtual machine CPU cores. Read more with the link on the screen if you're interested in running this in your environment. For the SQL Server DBAs, we can verify this quite easily. A visual way is with the SQL Server instance. Right-click on the instance, hit Properties, hit Processor, and expand the word All. You'll see the virtual NUMA nodes and their core assignments listed very clearly. It's a very easy way to spot check what is actually being presented to your virtual machines. You may find that this list does not exactly line up with what the Windows Task Manager is telling you. Trust SQL Server, not the Task Manager. If you're more T-SQL driven like me, you can also look at the DMV sys.dmos nodes. Run the query on the screen and you'll see the individual node IDs that correspond to your NUMA nodes. The online scheduler count is the number of CPU cores that SQL Server is able and willing to use per NUMA node. The online DAC means that we have a dedicated admin connection enabled. Chances are you should look into enabling this setting to reserve a connection for administrators if the instance ever has an issue. In the DMV here, it's safe to ignore that line. There's also a command line utility called CPU Core Info, which is part of the Microsoft sysinternal suite. It's a free download available at the link on the screen. It'll give you a logical to physical processor map, but in a virtual machine, hyperthreading is not presented, so you'll just see a one-to-one relationship. It'll also tell you the logical processor to socket and NUMA node assignment map, and at the end of the output is my favorite. It gives you an approximate cross-socket NUMA node access cost in terms of the performance overhead for managing our sockets and nodes. It's a really good way to quickly visualize and see just how much overhead we have between our sockets and nodes. Newer machines have much less overhead than older machines, but the difference is still there. You can use this free tool to help you confirm that everything looks good. Occasionally, I do find some odd anomalies with this utility. You can see in the screenshot here that we had a 10-core SQL Server. The hypervisor, which was not VMware based, was presenting one NUMA node with 2 sockets. The first socket had 8 cores, and the second just had 2. After doing some digging, we found that this particular hypervisor was very bad at presenting virtual machine NUMA. SQL Server was all messed up with its NUMA management and was performing poorly. We actually downsized the SQL Server to 8 cores, as Perfmon proved that they didn't need all 10, and we actually gained performance because we only had 1 socket to worry about with the vNUMA node. Yet another reason why vNUMA is so important is that your SQL Server and Operating System Edition might have some limitations in the number of sockets they can address. Both Windows Server and SQL Server Standard Edition, as of the latest versions, have limitations where they cannot address more than 4 sockets worth of CPU cores or a maximum of 24 CPU cores, whichever is lower. Let's think about that for a minute. If your virtual machine is configured for a high number of virtual machine sockets, both Windows and SQL Server might not be able to use all of the cores that you have assigned. Bad things can happen. Today, I am going to tell you about the worst case of virtual machine NUMA misalignment with the SQL Server engine that I have ever seen. A customer called up and wanted a routine SQL Server health check. Nothing too crazy, nothing fancy. They said everything was okay, not the fastest, not the slowest. The very first thing that I do is pull a perfmon trace. I just want to get a good sense of just what is this machine doing on a normal day. Take a look at the aggregate CPU percentile and average analysis over a normal week. Now, that's a really tight grouping. It's a little unusual. The interesting thing here, I asked him a very basic question. Is this business busy 24/7 or is it just busy 8 to 5? And the answer was it was only active 8 to 5 and everything shut down after hours. It's quite interesting. We've got a lot of activity after hours. So the next perfmon counter that I went and looked at is the split between the Windows kernel and Windows processes and the user processes. You can see these are stacked. At the bottom, blue and down, is the Windows kernel time. Above that, everything between the blue and the orange is what the user processes, including SQL Server.exe, are actually doing. That kernel time is off the charts. I freak out when I see more than 10% busy during business hours, let alone 35, 37, 38%. Something is clearly wrong here. Now take a look at the CPU consumption by core on a normal business day. If this doesn't set off red flags, I don't know what does. Half the cores are extremely busy across the entire day, which doesn't make any sense. More of them are completely quiet, and there's a handful that are in the middle just looking like normal. Something is desperately wrong here. This is not a balanced machine. I want to make sure that we don't have anything weird with the Windows layer itself, and you go look at the processor queue length counter, and on average, it's below 2. Not that big of a deal. Microsoft's guidance and my personal one don't really freak out until I see values greater than 3 times the number of CPUs as a warning and 5 times the number of CPUs as an alerting threshold. Okay, so the Windows layer is okay, so what's going on? I'm going to check one more counter. I went in and looked at processor information percent of maximum frequency. I first wanted to make sure that we weren't having any sort of Windows power scaling that may be artificially parking cores. But now notice, processor information parentheses number, comma, underscore total. That's your NUMA node number. This is a 16-core SQL Server. I've got 8 NUMA nodes. The physical machine that this was on is only 2 sockets. What's going on? Let's take a look at the virtual machine configuration. Now, I've mocked up this virtual machine to represent what I saw. It had 16 cores, which at first glance looked fine, but when you edit the virtual machine configuration, you'll notice it had 8 virtual machine sockets, each with 2 virtual cores. That's not cool at all. This virtual machine was running Windows Standard Edition and SQL Server Standard Edition. Both of them have an artificial license limitation of no more addressable compute resources than 24 CPU cores or 4 CPU sockets, whichever is lower. Both the operating system and the application server were unable to address half the CPU cores. They couldn't agree on which cores they couldn't use. So the Windows layer and the SQL Server layer were physically duking it out on this virtual machine and was resulting in absolutely miserable performance. We took an emergency maintenance window that night, took the virtual machine down, and went in and reconfigured it just for 8 virtual CPUs, because I knew we didn't need all 16, and reconfigured it for just 1 virtual machine NUMA node, so 1 CPU socket, 8 virtual machine cores. 4 clicks to go make this change. Now we let it run for a few more days. When we were done on half the core count, take a look at what the CPU consumption did after the change. That's a substantial difference. We are much lower than we used to be. Now take a look at the Windows kernel time. The only time it's above 5% is when we were running backups in the middle of the night, which is completely normal. During business hours, we're no more than about peak of about 6%. Not a big deal. Now take a look at the per core consumption on just 8 cores. They had one process that was running in the background that was pretty heavy on just 1 CPU. Everything else is perfectly normal. They had stuff running on 1 core with this process that was running in the background. Not much we could do about that, third-party application. But it wasn't really hurting anything. The SQL Server itself was perfectly fine and nice and low and reasonable with resource consumption. And then we go look at our processor queue length, and this thing is barely at 0.25% on average, with peaks a lot lower than what we saw before. Not only did we cut the size of this virtual machine in half, we sped up the SQL Server instance by over 3.5 times. By doing this, we allowed other virtual machines on that host to reduce their ready and co-stop times, measures of CPU scheduling, and we were able to repurpose that SQL Server licensing for a whole other machine that they were just sitting waiting to buy because they didn't want to spend the money. Now that is how you align a virtual machine with the physical machine NUMA topology. It doesn't have to be this way. You can get in front of these things as part of routine diagnostics to understand if some of the cores are imbalanced or not being used. Rerun the DMV query for OS nodes. Look at the number of node IDs that are greater than the number of sockets that you think are present. Take a look at the online scheduler count and CPU counts per NUMA node. What you find might surprise you. If you see that some of these cores are listed as offline, SQL Server or Windows will never be able to use those. It might be an artificial licensing limitation that you can address quite quickly. Another setting that can break your vNUMA is with the CPU hot plug feature of VMware. This setting allows for virtual machine administrators to be able to add CPUs to virtual machines without an outage window. For virtual machines that have burstable scalability needs, such as web and application servers, this might be advantageous. Usually, these servers are not really NUMA aware, so adding cores to them could result in a greater speed when needed. However, enabling the setting for SQL servers will explicitly disable virtual machine NUMA from ever being presented to that virtual machine. If you find that this has been enabled at your virtual machine configuration, understand why you might need this on a production server. If it's a really small SQL server that will never run the risk of expanding beyond the boundaries of one physical NUMA node, it might be acceptable to leave this enabled. All you have to do is type the word reconfigure in SQL Server to add those new cores once the VM administrators have done so. But if you ever need vNUMA for performance, or if the virtual machine is close to a physical machine NUMA boundary at this time, I would strongly discourage you from enabling this setting. Just be extremely careful with it, as it can have unintended consequences. You can see from the screenshot what happens when CPU hot add is enabled and virtual machine NUMA is explicitly disabled. No matter what you told the virtual machine to do with the cores per socket value, you get one and only one NUMA node. The differences of opinion in the task manager don't stop if this setting is actually used. You can see what happens if the virtual machine configuration versus what is actually presented. Task manager shows 2 sockets. SQL Server shows only 1. SQL Server is right and Windows is wrong. This is why you need to trust both the DMVs and utilities such as core info instead of looking at the crazy task manager. Let's throw another layer in there. SQL Server 2016 and above introduced a new feature called Automatic Soft NUMA. Scheduling a parallelized query on a lot of CPU cores is quite expensive and carries a lot of overhead. It looks like Microsoft has acknowledged this. If there are more than 8 CPU cores per NUMA node that the virtual or physical machine sees, SQL Server reserves the right to subdivide a NUMA node into smaller NUMA nodes to make parallelizing these queries easier. If you suspect that this is enabled on your servers, check out the error log immediately following an instance restart. You'll see an entry in the error log that says Automatic Soft NUMA was enabled because SQL Server has detected hardware NUMA nodes with greater than 8 physical cores. Think about this for a minute. If you set your max degree of parallelism to the number of cores in a NUMA node, and SQL Server is coming along and reducing the usable NUMA nodes for a given parallel query, either of these settings might actually backfire in terms of performance. Here's a quick war story about this one. A customer of ours had an 8-core SQL Server that was running SQL Server reporting services and a reporting database. Nothing too fancy. They had recently hired a bunch of people and the reporting workload was increasing. They decided that they needed 2 more CPU cores to help the demand. They increased the virtual machine from 1 socket by 8 cores to 1 socket by 10 cores. The physical machine had 16 cores per socket, so they were well within the confines of a physical machine NUMA boundary. However, automatic soft NUMA kicked in. It saw that they were greater than 8 cores per NUMA node and enabled soft NUMA automatically and presented 5 core NUMA nodes for us to use. Even though the max degree of parallelism was set to 8, they forgot to change that. SQL Server would only address 5 cores per parallelized report. Their reporting performance actually decreased as the available cores for a single report went from 8 to 5. Once they contacted me and we identified what was going on, they realized that this was an acceptable trade-off and changed their max degree of parallelism to just 5. Life went on, but they didn't question the difference anymore. The easiest way to check this is to rerun that diagnostics query. If you see node IDs that are different, but the memory nodes IDs are the same, chances are that automatic soft NUMA has enabled itself and is subdividing your NUMA node. Now, I'm not telling you to disable this setting or simply live with degraded performance if these scenarios apply to you. You can disable automatic soft NUMA with a trace flag if you need to. It's up to you to determine if leaving the setting enabled is appropriate for your workloads. One final setting to watch out for the virtual machine configuration is that the administrators can either set a reservation for available CPU for this virtual machine, or can set a limit to the amount of CPU that this virtual machine can use. Setting a reservation is not always the wrong thing to do, but I find that it can artificially limit the performance of other virtual machines on the same host, even if the CPU scheduling pressure is kept to a minimum. I recommend using resource pools at a macro level instead of reservations at a micro level per virtual machine because it's more efficient and it doesn't artificially hurt the performance of things if there are no other issues. Incredibly sneaky admins might try to set a CPU limit in megahertz. I absolutely despise this setting for SQL Server, even though I hardly ever see anyone using it. The setting could come in handy for pre-production servers that are doing nightly tasks that consume a lot of CPU, but I still claim that putting those virtual machines into a lower tier resource pool is more strategic instead of a limit. At this point, the only good thing that I see with this setting is playing pranks on other people, but that's just mean. Whew. Let's switch gears to virtual machine memory. Thankfully, virtual machine memory is a lot more predictable and straightforward to manage. As with any of this stuff, the virtual machine admins are used to managing all of your virtual machines as if they were regular general purpose workloads. Just like with CPU, memory and SQL Server have a much tighter relationship than normal VMs. Virtual machine CPUs can be carefully overcommitted as long as it's managed properly. Your VM admins might think that the memory layer is the same. When it comes to SQL Server workloads, though, you should never overcommit memory on the host. I think I've said that about 5,000 times now in this course. Most virtual machines do not consume the bulk of the memory they're assigned, but SQL servers certainly do with its buffer pool. If the memory is managed just like everything else, our SQL Server buffer pool can encounter some significant memory strain if the host memory resources are overcommitted and the host is in a memory pressure state. Therefore, again, never overcommit host RAM when running SQL servers and VMs. We spent a lot of time talking about right-sizing of CPUs, and we'll cover understanding the right amount of memory for your VMs in Module 11. We all know that SQL Server uses memory as a storage read cache and that most SQL servers have a pretty large memory footprint. Your virtual machine administrators are certain to challenge you on the memory footprint and at best will at least complain about it. That's natural and normal. They don't understand the SQL Server buffer pool, so it's up to you to educate them on why SQL Server has such a large memory footprint and how it works. The reason this is so important is that the way the hypervisor detects which virtual machines to target for memory reclamation if a host is under memory pressure, it's through the active memory counter. The active memory counter from VMware measures the amount of memory that has been read from or written to in the previous 20 seconds. VMware and a lot of the utilities around it are constantly looking at that number to make memory usage recommendations. However, this counter and these tools are not application aware. The active memory counter is inaccurate for our SQL Server workloads because it doesn't understand applications that do their own memory management. As a result, SQL Server workloads generally have a very high memory footprint and a seemingly very low active memory counter from the VMware's perspective. If the host is under memory pressure, chances are your SQL servers will be amongst the first targeted for memory reclamation. This state is extraordinarily bad for your SQL servers. If a SQL Server is targeted for memory reclamation, one of three things can occur, all of which can cause major performance issues. The hypervisor can elect to swap virtual machine memory to its disk, or it can attempt to balloon the virtual machine memory, or it can actually compress the memory used by the virtual machine. Let's talk about each of these individually. As a first wave of memory reclamation, the hypervisor will attempt to swap virtual machine memory to a virtual swap file on the same data store as the VMX file. Think of this similarly to an operating system being tight on memory and leveraging the page or swap file instead of continuing to consume OS-level memory. I don't care how fast your storage is, the fastest storage on the planet today is still at least one order of magnitude slower than the slowest memory. As a result, your SQL Server performance is guaranteed to start to degrade. The next level is memory ballooning. There is a very small utility that is installed with the Virtual Machine Tools package. It's called the balloon driver. By default, it's running, but it consumes almost no RAM at all. However, when a host is under memory pressure and this virtual machine is selected as a memory reclamation target, the hypervisor will instruct the balloon driver to inflate and demand a large amount of memory from the guest operating system. It does this at the highest possible priority inside the operating system. It knows that anything else on the operating system will start to give back memory and the guest OS will start to swap to disk. As soon as the host has reclaimed that memory, those blocks of RAM are redistributed to the virtual machine or machines that are demanding more memory. As soon as the memory pressure subsides, the memory is reallocated to the original virtual machine and the balloon is deflated. At that point, the operating system is aware of this state change and removes data from the page file and places it back into memory. I know you're well aware of how detrimental paging is to SQL Server performance. This is one of the last situations that we need. There's a subtle side effect that is going to shock you when I tell you. If the SQL Server instance level lock pages in memory is enabled, the SQL Server instance has the ability to lock the memory pages so that the operating system cannot manage or access or redistribute that memory. Think about that for a minute. SQL Server will not give up its memory. Therefore, everything else running in the operating system is going to drop straight to the page file. Your performance is going to get abysmal immediately in this scenario. The last level of memory defense is called memory compression. If the host is under so much memory pressure that it's going to start to get unstable, and the virtual machines on the host are not freeing up memory through ballooning quick enough, the host can then elect to compress pages in memory to free up memory space. This is even worse on performance than ballooning, as everything on the host is impacted because of the host CPU consumption to compress and manage those memory blocks. None of these scenarios are advantageous to performance, and there are plenty of reasons why we do not overcommit memory on the host at all. We have to make sure to maintain enough free host memory so that we can withstand one or more of the physical machines being removed from the cluster, either through planned maintenance or for unplanned failures. Now, let me give you one of the worst possible scenarios that I have ever seen with memory pressure. I was on site at a client whose line of business is significant wealth management. A couple of the virtual machine administrators took down 3 hosts in a host cluster of 12 hosts late in the morning on a Tuesday. They thought that there was nothing wrong with this as they were doing routine updates. What happened was that the DRS setting to balance memory by consumed instead of active memory was not checked. The hypervisor tripled up on the distribution of the virtual machines and placed too many VMs on the same host. The host immediately went into a memory pressure state. I'm sitting off to the side working with a couple of the DBAs when SQL Server Management Studio just suddenly went unresponsive. The biggest SQL Server on that host and in their business just dropped offline. The investigation afterwards was fascinating. The SQL Server instance had a very large memory footprint with lock pages in memory enabled. The host went into such a quick memory pressure state that it targeted the biggest SQL Server for memory ballooning, which was ours. The in-guest operating system gave back as much memory as it could come up with, but because SQL Server had locked its memory, the operating system had no more to give back, but the balloon driver was demanding more. The symptoms at this point were that the SQL Server itself seemed to be offline to the DBAs. Nobody could RDP into the SQL Server VM to see what was going on, but the operations team had a monitoring tool up that said SQL Server was up and running just fine. A 17-minute argument ensued about whether it was still up or down, all while customers were calling the support line to report that the wealth management platform was offline. The VM admins in the meantime reintroduced the host into the cluster in an attempt to regain memory for everything to spread out again. It did not fix the problem. What had actually happened was that the primary Windows VM was squeezed so hard that Windows ran out of memory for the TCP stack. All TCP connections were then severed. The application and our copy of SSMS dropped their connections. The monitoring tool, however, had a persistent UDP connection that was not cut. Technically, the SQL Server service was still online, and the monitoring tool reported as such. After the VM cluster had more memory available, a hard reset of the SQL Server VM brought it back to life a couple of minutes later. It was an absolutely horrible incident that resulted in a lot of explaining to do for all parties involved. A little bit of education for all the teams managing this platform would have gone a long way into understanding how to prevent this outage. The solution, again, is really simple. Never overcommit host memory, period. If there are situations where you must, I highly recommend setting the memory option to reserve all guest memory. It forces the hypervisor to never target this VM from the memory reclamation processes. It can look to the other VMs on the host, but not this one. I know it seems pretty harsh, and your VM admins might push back on this, but the potential instability in your primary SQL servers is the last thing that we want. Think about setting it for the most critical servers if this is even a remote possibility. If there's a chance of memory overcommitment pressure, maybe you could let it go after some of the less important machines. There is an interesting setting around being able to dynamically add more memory to your VMs. Unlike CPU hot plug, which will never allow vNUMA to be presented to a virtual machine, vSphere 6.5 allows you to enable memory hot plug without breaking virtual machine NUMA. I'm not so sure I'd recommend setting this by default, as you should be better managing SQL Server memory footprints, but if you need to enable this, you can safely do so. Simply running the reconfigure command in SQL Server will allow it to pick up the new memory footprint and then increase your buffer pool accordingly. I generally don't like to do anything to hot add, but if you do any of them, this is probably the safest. Just like with CPUs, memory has its own ability to set limits and shares. Also, just with CPUs, I prefer to use resource pools instead of either of these features. Using these can either put caps on the virtual machine that you can't really see from ingest, or limit or hold back other virtual machines even when resource scheduling pressure doesn't exist. Resource pools give you a more macro level way to manage scheduling pressures and do so without penalizing things when those pressures do not exist. Time to switch gears to virtual machine network adapters. Thankfully, this one is pretty straightforward as well. You have multiple types of virtual machine network adapters that can be added to a virtual machine. There's the E1000 and E1000E, VMXNet 2, and finally VMXNet 3. All modern operating systems come default with drivers that work for the Intel E1000 and E1000E network adapter types, and these are emulated within VMware. It's the default network adapter type for just about all virtual machines today. Unfortunately, the driver prohibits network throughputs from going above 1 gigabit throughput rates, even if you're on a 10 gig network or faster. You'll notice that I rarely make blanket recommendations with any of these modules. This is a blanket recommendation. Use the VMXNet 3 adapter type for all of your virtual SQL servers, period. This adapter is modern and quite fast and allows for throughput rates greater than 1 gigabit. The driver is included with the VMware Tools package, which your virtual machine admins should always install as the first thing they do after a virtual machine is provisioned. If you find that your servers were provisioned with the E1000 or E1000E type, you can retrofit an existing virtual machine with the VMXNet 3 network adapter type. It's not quite as easy as I would like. You'll need to document your network adapter settings. The network adapters are then removed from the virtual machine, which will remove network connectivity from your VM. You then need to enable Ghost Object View in the Device Manager and then show hidden devices in the Device Manager to remove the remembered definition of that hardware. Once you clean up the traces of the old drivers, then add a new network adapter to your SQL Server VM of type VMXNet 3. At that point, you reassign the IP, subnet DNS, etc., and it should be back up and running just fine. It's not the most fun, but once you do this a few times, you won't have more than a 5-minute outage to make the changes. One question that I get asked a lot is if we need to have multiple network adapters teamed inside the virtual machine for redundancy, especially if the SQL servers are in a highly available configuration. The network adapters connected to the virtual switches that your VMs are assigned to should already be redundant. Because of that level of redundancy that's transparent to the virtual machine, I generally find that we do not need to add multiple network adapters for redundancy to the virtual machine itself. I usually say assign one virtual machine network adapter per purpose. Keep in mind that you can have multiple purposes for network adapters on virtual machines. You could have a network adapter for primary server traffic. You could have a different network adapter assigned to a database backup network that's isolated from the rest of the environment. You could have a Windows Server failover cluster heartbeat communication stream isolated to just a separate network adapter, just like you could have the replication traffic for availability groups. I'm all for isolation of workload types, especially if security is involved. It gives you the easier means to monitor the traffic on each network adapter as compared to trying to sift through all that traffic on one network adapter. Now, I said all that, but I find in practice that just about all the SQL servers that I see in the field have just one network adapter assigned to them, and that works just fine. Assign the network adapter or adapters that you need to serve the purposes that this machine will fulfill, but don't overcomplicate things. Follow your same basic practices as your physical servers, including firewalls and network routing. Remember the VLANs that we talked about in a previous module? Your virtual machine administrator will create a virtual network that allows assigning a virtual network to a virtual network adapter. This is a great mechanism to help you isolate and segment your network traffic. It could be that you want to put a SQL Server in a DMZ. It could be that you want to route your SQL Server backups to an isolated network for security. It could also be that your regulatory compliance requires that any data that may contain PII be placed on a network that has security scanning. Lots of scenarios would necessitate multiple network adapters and multiple virtual networks. You have lots of flexibility to define your virtual networking as your business requires. Okay, we have finally gotten to virtual disks. Virtual disks are rather complicated, so we're going to take some time to go through the virtual disk component. There are many ways to present storage to a virtual machine, although not all are created equal. The primary virtual disk format is called the VMDK, which is simply short for virtual machine disk. This is the preferred presentation method for storage for virtual machines, as it allows the hypervisor to have full control over the virtual disk and provides a lot of functionality to the virtual machines. However, maybe we have certain functions inside the virtual machine that require the use of a SAN LUN directly. The different hypervisors give us the ability to pass a SAN LUN directly through the hypervisor and attach it to a virtual machine. This is called a pass-through disk. VMware calls this a raw device map, or RDM disk. There's also a newer construct called a virtual volume, or a vVol. A vVol allows the hypervisor to treat a raw SAN LUN as a virtual disk, but leverages vendor-specific APIs to translate the request directly to a corresponding LUN on the SAN. The last means is some form of in-guest connection, such as iSCSI or SMB3 or even NFS. Let's talk through the specifics on each of these and come up with the right use cases for all of them. We're going to start with VMDKs. The primary storage for virtual machines is usually the virtual disk, or VMDK. Technically, it is a file on the underlying shared file system. These can be grown up to the space of a data store or 62 terabytes, whichever is lower. You can see on the screen here under the disk file for this hard disk a data store name, then a path, then a VMDK name. You can also see that this is hard disk 3 and that it's 800 gigabytes in size. It has a maximum size listing on it of 2.6 terabytes, and that's because that's how much free space is left on that data store. When we add a virtual disk to a virtual machine, we have 3 different ways to provision it. This is for block storage only. We can provision it in a format called Thick Provision Eager Zeroed, or TPEZ. We can also provision it Thick Provision Lazy Zeroed, or TPLZ. We can also thin provision it. Let's take a look at these and figure out which we should be provisioning our disks as. The first provision type is Thick Provision Eager Zeroed. This disk is fully provisioned on the underlying data store prior to you being able to use it within the virtual machine. It's similar to the way SQL Server does object provisioning without instant file initialization being enabled. If we provision the disk in this format, all of the space that encompasses this virtual disk will have zeros written over it before the disk is available to use. When you provision a disk, it can take a little bit of time to complete the new disk creation process, depending on how fast your storage array is. Afterwards, however, there are no additional overheads for accessing this underlying disk. Let's walk through an example of this. I create a new virtual machine with 2 virtual disks where the C drive is 120 gigabytes and the data drive is 500 gigabytes. Our data store that we place the data virtual disk on is 10 terabytes with nothing else on it. Because we have thick provisioned this virtual disk, it consumes all 500 gigabytes on the data store, and we have 9.5 terabytes free on the data store for other virtual disks. I can't use this virtual disk until the VMware process is done writing zeros to fill up this 500 gig virtual disk. The next provision type is thick provision lazy zeroed. It is eventually fully provisioned on the data store. The disk is allocated logically as a full disk, but all consumed space is overwritten with zeros after that step completes. It has potentially less provisioning time than thick provision eager zeroed, and after the storage level zeros completes, there's no additional overhead for us using that storage. Take the previous example and let's deploy it as thick provision lazy zeroed. The end result is still the same, but a virtual disk is available to use a few minutes sooner. It's still running zeros in the background while you start to use it. The data store free space is still the same, and once it's done writing zeros, everything else is essentially the same. The last disk type is thin provisioned. It is logically allocated in full, and your guest operating system sees it as if it were completely provisioned. However, it only consumes on the data store what it actually consumes in guest. As the disk is filled up inside the VM, the consumed space on the data store grows. If a new block inside the virtual disk is attempted to be written to, since it has never been written to before, the hypervisor will take some time to write zeros into that new block. It has the least amount of time needed to provision the virtual disk, but there's a small overhead inside the virtual machine while it waits for these blocks of zeros to be written after the virtual machine is fully in use. Take the previous example and now provision the virtual disks as thin provisioned. Inside the virtual machine, all three of these look the same. However, with thin provisioning, the actual data store free space is only what is consumed inside the virtual disk. In this case, if 170 gigabytes have been consumed on that virtual disk, then just 170 gigs are actually used on the data store, and we have more free space than we had before. Thin provisioning can cause some significant challenges if it's not managed properly. If a VMware data store fills to its maximum capacity, all of the virtual machines on that data store get suspended or paused, waiting for administrators to add more space. That's an absolutely horrible situation to be in. Appropriate management and monitoring can minimize the chances of an outage associated with the data store filling up. While I'm not completely opposed to thin provisioning of virtual disks, a thin provisioned SAN LUN with thin provisioned virtual disks can cause even more challenges. If it's managed properly, however, it's not that big of a deal, but unfortunately, that's a big if. My recommendations are that all production SQL servers have thick provisioned eager zero disks connected to them. If they must be thin provisioned, I only think about this if the underlying storage is either flash or NVMe, and if it's monitored and managed incredibly carefully. There's still a tiny amount of performance overhead when compared to thick provisioned eager zeroed, but on a very fast storage subsystem, this is usually barely even measurable. One of the historical challenges for VMware is that we could not use a shared virtual disk for Windows Server failover clusters. It was not supported and could cause issues if it was attempted to be implemented. That's why historically Windows Server failover clusters with shared storage were traditionally dismissed by virtual machine administrators. VM admins had to resort to raw device map storage for shared storage for Windows Server failover clusters, and this created a lot of extra overhead and work for them. vSphere 7.0 recently introduced a new shared virtual disk model that complies with the SCSI 3 format that Windows Server failover clusters require to be able to lock the disks. The shared disk feature currently only works for fiber channel connected storage. It must also be thick provisioned eager zeroed on a dedicated clustered data store underneath. This does give us the ability to use a shared disk for Windows Server failover clusters, but at the time of this recording, it's a pretty high bar set to be in a supported state with this configuration. Okay, for those of you that might not be on vSphere 7.0 with a fiber-connected array that needs shared storage between multiple VMs, let's talk about raw device maps and why your VM admins hate them. VMware calls the act of directly connecting a virtual machine to a SAN LUN a raw device mapped disk, or RDM. You can see from this diagram that virtual machine B is using traditional VMDKs that are placed on a VMware shared data store, which is essentially a formatted SAN LUN underneath. Virtual machine A has a raw device map disk through the hypervisor directly connecting to a SAN dedicated LUN just for that disk for that virtual machine. This pass-through model of the virtual disk gives us a handful of benefits and a number of drawbacks. The benefits are that the virtual machine can then talk directly to the SAN LUN to use specific features on the SAN that might be beneficial, such as SAN LUN level snapshots. There are two types of RDMs, physical and virtual. A physical RDM has no abstraction layer within the hypervisor and is directly connected to the SAN LUN. The virtual machine can then lock the LUN to do whatever it needs to do. Physical RDMs are quite useful for Windows Server failover clusters and SQL Server failover cluster instances when you need shared storage that one node can lock. A virtual RDM adds a little bit of abstraction within the hypervisor while continuing to pass through the commands to the underlying SAN LUN. It is treated a bit more like a virtual disk, and the hypervisor can then sample and record performance statistics for this disk. It also allows us to perform some VMware layer features, such as taking disk snapshots or storage vMotions, which can be helpful for migrating virtual RDM storage into traditional VMDKs. This is really helpful for SAN migrations. As a virtual machine administrator goes, though, neither are good options. It creates a lot more work for the administrator to present and manage these pass-through disks. Just mention RDM near a VM administrator and listen to them groan. More modern storage devices support a new construct called a virtual volume, or vVol. A vVol is a very fascinating development. It's an advanced storage API that allows SAN LUNs to be created and managed by the virtual platform and presented and used just like virtual disks to the VM. The advanced API is a layer that performs the translation between the different components in the system. It is storage protocol independent, but your storage must support the virtual volume standard. vVols are incredibly useful for easily presenting and managing shared disks underneath Windows Server failover clusters. It now helps the storage itself understand the virtual machine workload and reduces data store metadata contention. Just like with SQL Server and anything else, it has a lot of different access points to the same object. Virtual machine data store metadata contention does exist and can cause delays in storage access. Since it's actually a SAN LUN underneath, the layer of locking and blocking no longer exists. While I still want you to use a traditional virtual disk, vVols are quite compelling if you need shared storage underneath the virtual machine. The only drawback is that your storage has to support it, and your virtual machine's administrators need to know how to manage it. The last storage type that we're going to talk about is in-guest presented storage. In-guest presented storage is when you use the guest operating system to connect to external storage for use by your SQL servers. This can include block-level devices such as iSCSI targets. It can also be beneficial for network shares such as SMP3 or NFS targets. All of these allow you to leverage SAN LUN or shared level features. I really don't recommend in-guest storage presentation unless you absolutely need it because it creates a whole different set of challenges. This is going to lie a little differently with what some storage vendors out there tell you. Some storage vendors' best practices state to use in-guest iSCSI to connect to their storage arrays. I find that in most cases, the underlying features of the storage that aren't the same as a virtual machine layer are never used, and the complication and performance overhead of this architecture is simply too high. As a result, test in your environment which works best for you. I prefer the simplicity of virtual disks when at all possible. In order to successfully maintain the performance, you almost always have to have dedicated high-speed network paths on the physical machine itself just for this virtual machine's network connections. This means additional network adapters at the physical machine, separate virtual machine networks for storage presentation to the guest, and now in-guest level network redundancy. It's a tremendous amount of extra overhead, and I highly doubt the benefits that you're looking for will outweigh the complexity and the challenges of troubleshooting something as complicated as this architecture. Plus, in-guest storage connectivity will usually not buy you any additional performance. Neither will raw device maps. VMware has performed a lot of testing and validation over the years and have concluded that there are no noticeable performance differences between virtual disks and raw device maps. vVols can reduce data store metadata contention, but this shouldn't be an issue anyway, and you should have this under control. The reason I present all of this is that there are always use cases that align better with any of these features. Otherwise, none of these features would exist. Take the storage presentation that best fits your requirements and matches your workload needs, and make sure to test appropriately that this is the right disk presentation for you. Storage presentation is not the only part that we have to worry about for the virtual machine storage. We also have to worry about these storage controllers, or the mechanism used to connect the storage to the virtual machine. Let's dive into that. All connected storage to a virtual machine, as long as it is not in-guest originating, must use a disk controller to connect that storage to the virtual machine. It's the exact same architecture that applies to physical servers as well as public cloud. One interesting thing to realize here is that the virtual machine guest operating system and the hypervisor do storage level queuing not just by disk, but by disk controller as well. VMware has a number of options for us to present virtual disks to a virtual machine. Some of these are not available on more modern versions of the VM itself, but all are present. However, these are not all created equal, just like with everything else. The first set is the LSI Logic Parallel and SAS adapters. These types are present for compatibility. The disk controller inside the guest operating system is almost always available for these controller types without any additional extra work from us. The driver is just included with the guest operating system. VMware leverages this for compatibility's sake, so you don't have to do anything fancy to get the virtual machine to boot up for the first time. However, these are present for compatibility and ease of use, but not necessarily performance. The same thing goes with SATA, bus logic, and IDE controllers. These are present for older VMs, but we should never use them for our SQL servers. The two that I do care about are the Paravirtual SCSI or PV-SCSI and NVMe controllers on the VMware platforms. Let's dive into all of these to figure out why some are better than others. The LSI SAS controller is built into the Windows and Linux operating systems natively as part of their core. They're simply there for compatibility purposes, but certainly not for performance. They have a single storage activity queue with a queue depth of 32 operations. For some underlying storage types, this queue depth is just fine. For faster storage, however, this queue depth is far too low and can be underutilizing your fast storage's performance. The PV-SCSI controller, on the other hand, is included with the VMware Tools package. VMware built this controller many years ago to boost performance and includes the driver with the VMware Tools package. It has better performance when on flash hybrid, all-flash, or NVMe-based storage. In practice, I see faster IOPS responsiveness, higher throughput, lower latency to storage, and lower CPU consumed for storage activity inside the guest operating system. It has a default storage queue depth of 64 operations, and the registry setting can be overriding this value up to 254. Whatever you do, do not blindly update this setting to the maximum. VMware's knowledge base article is not very clear that you should not just set this all the way to the top. If you bump this all the way to the top, and the underlying storage queues have not been improved as well, you end up putting the hypervisor into a situation where even more storage is stacked up inside the hypervisor, and you can actually see higher latencies in guest than without. We'll talk more about this in the performance module. One good thing to note is that driver updates for this controller type are now accessible through Windows Update. If you're on all-flash or flash hybrid storage, this is the controller for you. The last controller we're going to talk about is the NVMe storage controller. Only consider this controller if your underlying storage is based on the NVMe storage protocol. It has 16 storage queue, 1 as an administrative command queue and 15 for storage commands. It has a maximum queue depth of 256 with 4,000 in-flight commands per controller. What all this means is that if your underlying storage is based on the NVMe storage protocol, you have a much greater ability to send many more concurrent commands to the storage and have it processed in a reasonable amount of time. This controller is capable of much wider storage access requests and can better take advantage of the improvements in this type of underlying storage. On the VMware platform, you can have up to 4 SCSI or SAS disks controllers assigned to a virtual machine. You can also have up to 4 NVMe controllers connected as well. You can have others that are SATA or IDE, but they have incredibly low queue depths and should not be used unless you absolutely have to, and really then only for archival data. Now remember a minute ago, I said that VMware not only does storage level queuing by disk, but by disk controller as well. If we have 4 or more virtual disks connected to the virtual machine, we want to use as many controllers as we can fit to improve the I/O queuing fingerprint of this machine. Virtual disks get assigned to a virtual disk controller through the setting at the virtual machine layer called the virtual device node. You can see there's a setting here for disk controller 1, hard disk number 3. You can see the disk assignment there next to the word hard disk 3. In this image, it's represented as SCSI 1:0. Since all of these start with 0, this image shows that the disk is connected to the second controller and the 4th slot on that controller. As of the latest version of VMware, you can connect up to 60 disks with the LSI SAS controller type or 256 disks with the PV-SCSI controller type. You can add an additional 60 NVMe disks to the virtual machine. Think about that. If each virtual disk's max size is 62 terabytes, and you can have over 300 of these disks connected to a single virtual machine, that is an incredible amount of storage presented to a virtual machine. That is certainly not saying you have to provision this number of disks. I do want you to understand the relationship between the controller and the virtual disk and the distribution of your SQL Server objects. We have fixed queues at the controller level for the virtual machine disk. The operating system will also do the queues at the disk layer. What I really encourage you to do is to explore multiple virtual disks to help spread out your workload. You can see on the diagram here a sample distribution of SQL Server objects. This diagram is similar to what we've been doing on physical servers for quite some time now. In this diagram, we spread out the operating system disk, have the SQL Server instance home on a different disk, and move our system databases to a third disk just in case we're doing something active like availability groups or transactional replication. We'll then provision one or more disks for our SQL Server database data files. We'll then provision one or more disks for our SQL Server log files. We'll then have at least one disk for TempDB, and if your TempDB workload is significant, probably have more than one of those to spread out the workload. If you're doing local backups, then add another disk for that too. I know it might seem like a lot, but these queues can stack up very quickly. Having a wider distribution of data here will shove the storage access bottleneck further down the infrastructure stack. We're going to talk more about this in the performance module. The good part about this model is that it gives you a standard means to standardize your deployments the best that you can. The only thing that I would differ between large and small scale deployments would be the number of data, log, and TempDB disks. Just like with CPUs and memory, the storage speed can also have the same resource allocation shares or IOPS limits. As with before, I don't recommend using these as I love resource pools for resource scheduling prioritization without penalizing things when no scheduling pressure exists instead. There are some very special considerations when using a SQL Server failover cluster instance on the VMware platform. Let's talk through a few of those now. When using shared RDM or vVol disks for Windows Server failover clusters, newer versions of VMware will allow you to vMotion virtual machines in this configuration without causing an issue. Earlier versions of VMware would not allow you to vMotion these and maintain a supported state. And just like I mentioned a little bit ago, shared virtual disks underneath Windows Server failover clusters, and more specifically SQL Server failover cluster instances, are now supported as of vSphere 7.0 as long as you're using fiber channel connected storage. There are some extra considerations around the virtual machine architecture that I do want to mention before we go to the next module. Some of these are 1 in a million chance things to monitor, but when you hit enough of them in production, it's worth mentioning as these are preventative steps. A very overlooked component that is quite easy to maintain is that the VMware Tools package needs to be kept up to date. Your virtual machine administrator should be keeping this up to date, and every time they do host level updates, it usually accompanies with a new VMware Tools package. These need to be updated across the entire environment. It can very briefly interrupt network communications to a given server, so these should be updated during maintenance windows. Thankfully, the storage controller is now being updated through Windows Update, so this is not as impactful as it used to be. I still recommend doing these updates during maintenance windows because you don't need your SQL Server communication getting interrupted. The next setting is one of the ones that really bothers me. There's a checkbox in the virtual machine configuration that says synchronize the virtual machine time with the host time. It's unchecked by default. We do not want the host syncing the guest time because we want our SQL Server high availability configurations to pull things from Active Directory. However, even if that box is unchecked, VMware will still synchronize the in-guest time on a number of different scenarios. It does it during a vMotion when a snapshot is taken or removed, or when the VMware Tools service inside the operating system starts or restarts. These scenarios don't sound like much, but if a host time has drifted a little bit and is out of sync by more than just a small amount, it can wreck your SQL Server high availability architecture. I have seen this setting take out failover clusters and availability groups alike. The link on the screen takes you to a VMware knowledge base article that describes this scenario. You know this concern has been around for a while. As the time of this recording, the VMware knowledge base numbers are in the 8 digits. This knowledge base entry is 1189. I think they started at 1000. To forcibly remove the VMware Tools service's ability to sync the in-guest time with the host, add the following commands into the virtual machine advanced configuration parameters. Each one of these will disable it for a certain scenario, so pick and choose the scenarios that you think are most likely for your environment. I usually do all of these for any SQL Server that's in a highly available configuration in my virtual environment. I also do all these settings for things other than SQL servers, such as domain controllers, Microsoft Exchange nodes, or anything else that's highly available. The next setting is somewhat experimental, so if you even think about doing this without testing, you are crazy. Modern hypervisors tell the virtual machines that they are virtual machines, and the virtual machines know how to listen for this. Occasionally, I find that the operating system is behaving a little bit differently than if it did not know it was a virtual machine. Specifically, in this case, Microsoft instructs Windows that it supports the Microsoft Hypervisor interface for the operating system. Occasionally, I find that ultra-sensitive, low-latency applications behave better when this communication is disabled. The two commands in blue on the screen here, hypervisor.cpuid.v3 and v2, can be set to false. In my consulting career, I've only needed to set this just once. Test and validate that if you decide to enable this setting, that it actually makes a difference. We are going to build a new SQL Server virtual machine in the way that I like to see the defaults built. If you don't already have a template to work from, create a new virtual machine. Name it according to whatever naming convention you have in your organization. Pick either the cluster or the host you want to drop it onto. Pick the data store you want this placed on. Set the compatibility to the most current you can possibly get, and then make sure to set the guest operating system to the version of the OS that you're running. Pick the number of CPUs you want. Now, don't stop there. Go fix the virtual machine NUMA. It defaults to some really silly values. We want it to line up with the physical NUMA topology. In this case, 1 socket by 4 cores. This template, we want 16 gigs of RAM. We're going to put our C drive at 120 gigs. The default template is LSI SAS. Pick the virtual machine network. Now, we need to install this from Windows, so we're going to pick an ISO image on one of our data stores here to boot from. Make sure to connect it so we can boot properly. Now, before we go to VM options, the next thing we want to go do before we go to our VM options is add our SCSI controllers here. This is going to go on an all-flash array, so we want to use the type paravirtual. We're going to go ahead and add all 3 here. They default to LSI SAS, so expand this out, change this down to VMware paravirtual. We'll change the C drive controller a little bit later. Now we'll go ahead and add our virtual disks. We're going to add 5 more virtual disks. We'll add the disks, then we'll change the sizes, and then we'll assign them to the correct controllers. We'll go 10 gigs for the SQL install home, 15 for our system databases, 100 for data, 60 for log, and 40 for tempdb. Each one of these we're going to then provision on this particular machine. Again, it's up to your environment. The first 2 we're going to keep on the primary controller, SCSI ID 01 and 02. For the next 3, we're going to use SCSI controller 1, 2, then 3. So each of these have their own controller. You can see there the virtual device node, SCSI ID 10. Same thing for disk 2. And the same thing for disk 3. Now we're going to go and make sure that we're going to use the VMXNet 3 adapter for our network adapter. Now go up to VM options. We're going to go to the VMware Tools tab, and we're just going to double check that synchronize time periodically is not enabled. Then go to boot options, quadruple check that your firmware says EFI, and this is before you install the Windows operating system. Now hit next and finish. At this point, power the virtual machine on. We are good to start installing your operating system. Now, through the magic of accelerating this recording, we're going to install Windows really fast here. You'll notice when we go to select our disk where we want to install it, anything connected to one of the paravirtual controllers does not appear. This is by default because we don't have the VMware tools installed yet, so that driver doesn't exist. This is why I usually choose to install this to the LSI SAS controller and then go change this after the fact. Now, we'll just sit back and let this thing work. Shouldn't take too long. Okay, this virtual machine is now up and running. You don't have a network adapter or an advanced disk controller yet. So the very first thing that we want to do is go ahead and log into it, and we are going to install the VMware tools. Nothing too exciting about the install. It takes a couple moments and then you reboot the machine. All I did there was unmount the SQL Server ISO. It's a good practice to get in the habit of. At this point, your virtual machine is good to go just like normal. For the prudent individuals out there, this would be the time to shut down the virtual machine and change the disk controller on the C drive, SCSI controller 0, from the type LSI Logic SAS to the type VMware Paravirtual. This makes sure that all of your controllers are type Paravirtual and you are now good to go. We'll talk about what next to do in Windows in the next module. Whew, that is certainly a lot to take in. Next step, we're going to work on tuning the Windows operating system. Stay tuned. Maybe get some coffee.